Welcome to a lesson with Dr. Powell. How can we show that the limit of a function is not something? We've been talking rigorously about how we can show that it is equal to something and verify it. But what about if it's not something? Like, for instance, right here, something like this. How can we show that this function is not equal at that point? Let's give a specific example. Suppose we have a piecewise function. So let's just make it very simple. Let's just do f of x is equal to the absolute value of x divided by x. Now, written as a piecewise function, this is going to be 1 for x is bigger than 0, and it's going to be -1 for x is less than 0. Okay, so how can we verify rigorously using epsilons and deltas that the limit as x approaches 0 of f of x does not exist? Well, for one thing, um, we could let's just draw a picture. That's usually the best way to do it. So let's work with that. So we go -1 up to this point, and then we go 1 past this point. Okay. Now let's just pick anything arbitrarily. It doesn't matter what it is. In fact, but maybe it does. Let's think. Well, we know what the left hand and right hand limits are, and let's assume that. So let's take this right here. All right. And just think about this point for a minute. Let's take an epsilon up and down. In the picture, it's easy to see that this point, that points up here, are outside the function. So how can we say that? Well, maybe what we could say is, given epsilon, and even make epsilon less than 1, given epsilon greater than 0, that is also less than 1, so it kind of is described in the picture, then given any epsilon, or any delta, that is, so we say there exists a delta. Well, let's just take every delta and show that it fails for every delta. So given delta greater than 0, then here's an idea. What if we take then if x, so let's think about that in the picture. Let's go off and see what the problem is going to be that we're going to talk about. If we go out delta that way, what if we take an x value on this side of delta in between 0 and delta? In fact, we could just say delta over 2. Then if x is equal to delta over 2, what happens? Well, let's just plug it in the function and see. Then if x is equal to delta over 2, f of delta over 2 is equal to, and we can use the idea of the piecewise function definition here. Since delta over 2 is positive, we're going to get a 1. And then we can say, but then let's find a contradiction with that idea. What does that mean? So, because we're saying that the function's up here, so how do we say that's outside the box? Well, why don't we just go to the definition of what it means to be in the box rigorously? So we know that f of delta over 2, what minus, then the target value down here is actually -1 for the y, minus a -1. Let's see what this is equal to in absolute value. So f of delta over 2 is equal to 1. So we have 1 plus 1, which is equal to 2. But what do we know about that? We made an assumption that epsilon was less than 1, right? Which is greater than 1, which is greater than epsilon. So that's a contradiction right there. That's a little symbol for contradiction. But what we showed is that given epsilon greater than 0, that is also less than 1, all right? If we gave any delta value, we found a delta, then we found an x value between 0 and delta on the right side, and we plugged it into the function, we got something, and we saw, hey, that was out of range. That wasn't in the y tolerance. And delta was arbitrary, it didn't matter. So there is no delta that works. So there doesn't exist any delta that works. I mean, visually, we can see this quite clearly, but also this is a little description of how it would work rigorously. I'm not going to require you to be able to come up with something like this on your own, but I'm only putting it here just pretty much for experience and culture, just so you can look at it, and maybe I'll ask a question about it or not. I'm not sure at this point, but I hope that kind of gives you a little bit more intuitive sense for how these rigorous definitions and statements of limits can be used logically in order to show different things. Thanks for watching.